We have a world polluted with sensors. Due to technological advancements, sensor systems are getting smaller and smaller, and they are seamlessly integrated into things of everyday life to sense the physical world. They are integrated into shoes, jackets, and environmental objects like cookers, dishwashers, or microwave ovens to sense their physical status. So the sensors are already out there monitoring us and the environment. We just have to select the sensor entities that are available to sense for activities and context. We call this approach opportunistic sensing. We use sensors that just happen to be available rather than predefining them at design time of the system. To deal with the vast heterogeneity of sensors, we use sensor self-descriptions to identify the capabilities of each sensor. As exemplarily shown with the motion jacket left upper arm X-sense sensor, the self-description is split into a dynamic part that holds the information valid for this very sensor entity, like the sensor ID, its technical ID, and the trust indicator. Additionally, in so-called experience items, the information about the used machine learning techniques and the labels the sensor can be used for and to which extent, as indicated by the degree of fulfillment, is stored. The technical self-description is fixed for each type of sensor and states its physical characteristics like its technical ID, its manufacturer, its model number, and its sensing hardware-related properties like the range of the update frequency. So each sensor describes its capabilities and can be queried for it. Sensors have different working characteristics, measure different environmental quantities, deliver different types of data, and can be of physical, logical, or virtual type. As shown in our example, we have Bluetooth acceleration sensors, inertia cube-free sensor systems, sunspot acceleration sensors, microphones,
hydrophones, hygrometer,
and magnetic reed switches. To access the different sensing devices, we use sensor abstractions that provide the complete functionality of the sensing device to the system, but hides and encapsulates its hardware and low-level access details. Using the self-descriptions and the sensor abstractions, each sensing device can be invoked in the same manner as it describes its capabilities and offers a wrapper to get access to its data. As people do not want to be bothered by selecting sensors manually, we defined a system architecture that automatically selects the best set of sensors. Activities that should be sensed for are stated as recognition goals to the system. The framework automatically configures an ensemble, which is the best set of sensors that can contribute to the goal and reacts on changes in the sensing infrastructure at runtime. The Opportunity framework abstracts the sensors available in the environment and shows their configuration and status. The green bubbles symbolize the available sensor systems, and the red rectangle the recognition goals that are sensed for. When a recognition goal is stated to the framework and translated to a sensing mission, the available sensors are queried to get knowledge about which sensors can be used, as indicated by the blue flags. Each sensor that can be used according to its self-description responds in how good it can contribute to the recognition goal. The response of the sensors are analyzed by the framework, and an ensemble is configured as indicated by the red flags and the data streams. The framework sketch connects the sensors configured to an ensemble to the sensing mission using an arrow indicating the flow of data. As sensors can appear and disappear in natural dynamic environments, the framework has to react accordingly to fulfill the opportunistic approach in reconfiguring the best ensemble. If, for example, an on-body sensor disappears as a person is walking into another room, the framework notices the disappearance of the sensors, colors the illustrations gray, and disconnects them from the sensing mission. As the framework has the knowledge of the sensors, it analyzes which are still available to contribute to the goal, indicated by the blue flags, and configures the best ensemble. When a sensor appears, the framework checks if the sensor has already been known by the system, as symbolized by the gray bubbles. If this is the case, the framework has all the information needed to reconfigure according to the appearance of the sensor if a better ensemble can be found. So it selects the appeared sensors attached to the jacket and configures them as the new ensemble because they can better contribute to the goal as the two other sensors. As there is a big number of sensors available in the environment, not all can be pre-trained to recognize certain activities. Therefore, one of the features of the Opportunity framework is to detect learning candidates for a recognition goal during runtime and train them with the labels that are produced by the current ensemble using transfer learning. During runtime, the framework checks if sensors are available that have a label corresponding to the actual sensing mission with a degree of fulfillment of 0. If the framework detects such a sensor, like the shoe sensors of the person, indicated with the orange flags and the recoloring of the sensor bubble to orange in the framework sketch, this learning candidate is connected to the sensing ensemble in a way that it is being trained with the labels generated from the ensemble of the sensors attached to the jacket. The labels sit, walk and stand are transferred to the shoe sensors, and the quality of the learning process is checked according to the comparison of the output of the teacher and the learner that is done periodically after a certain amount of time. After the learning process is finished, the framework writes back the degree of fulfillment for the learned labels and the learned classifier chain. The self-descriptions are now colored blue as the sensors can now contribute to the goal. The framework disconnects the learner that can now be used to detect the recognition goal. As sensors are sensitive due to changes in their position, the Opportunity framework is capable of detecting faulty data being delivered by a sensor that changed its position, got rotated, or is malfunctioning. Each sensor is aware of how plausible the data it delivers is. This reliability measurement, called trust indicator, indicates the self-awareness capabilities of the sensor, describing how plausible and trustworthy the data it delivers is, as a value between 0 and 1. If the position of the sensor gets altered, if for example a person grasps a distance object, we use anomaly detection to identify the faulty sensor, as sketched by coloring the one faulty sensor purple and changing its trust indicator accordingly from 1 to 0.2568. As the trust indicator falls beneath a defined threshold, the Opportunity framework reconfigures the ensemble and excludes configurations using the faulty sensor. Now the shoes are the best ensemble to recognize the stated goal, thus the framework reconfigures and uses the shoe sensors as ensemble. The opportunistic approach allows us to use sensors that are already polluting our environment, instead of integrating more and more application-specific sensors that are predefined at the design time of the system. We can use sensors that just happen to be available, thus reducing the load on users and environments to install new sensors for each application. The challenge altered from deploying application-specific sensors to the utilization of the already available sensor infrastructures in an opportunistic way to make the world a little bit smarter.